Okay, my friends, so here we are with part 2 of Thursday's class. So we did our warm-up, and now we're going to take a look at just 4 more U substitution problems. Again, feel free to fast forward, rewind, pause, but I really want you to do the problem before taking a look at my solution, except for this first one we are going to do together. So basically, here's the situation. We're asked to integrate sine cubed x, and I just want to remind us that that just means sine of x all cubed, right? Sine of x times sine of x times sine of x. And basically, here's our situation, is we only know 3 methods to integrate, right? We know, like, I can just look at it, right? Like, you see the integral of 1 over x, and you hopefully know that that's natural log of x, because the derivative of natural log of x is 1 over x. We have, like, reverse power rule. So this would be natural log x dx is natural log x. You can just look at it and tell. We have reverse power rule, so say we had 3x to the 4th. We know that that's going to be 3/5 x to the 5th plus c. And then we have usub. And the thing with usub, remember from day 1, is that you need to be able to see the derivative in the problem. So here, if you're telling me I have sine of x cubed, well, somehow I need to make cosine of x appear in the problem, because this is not one that I can just look at it and tell. If you think you can just look at it and tell, I would push you to see why you're not correct. I think one common response would be 1/4 sine of x to the 4th. But remember then, if you were to take the derivative of that, yeah, the 4th and the 4 would give you 1 that you need, and it would give you sine cubed. But then you would have to multiply by the derivative of the inside, right? So that's not going to work. So you can't just look at it and tell. You can't use reverse power rule, and we only know usub. So we got to find a way to make cosine appear in this problem so that we can use usub. So how can we make cosine appear in this problem? Well, hopefully you remember your one trig identity that everyone should remember, even if they don't remember all the other ones, because I don't remember all the other ones. But sine squared plus cosine squared equals 1. Right? Remember, this is the same as saying sine squared plus cosine squared equals 1. So what can we do? Well, we can break sine cubed up into sine of x squared times sine of x, right? That's still equal to sine cubed, right? This is still the same as sine cubed. And now from here, I can break this up even further, and I can take sine of x squared and say that sine of x squared is going to equal to 1 minus cosine of x squared, or if you prefer to write cosine squared x. So I'm going to replace the sine of x squared with 1 minus cosine of x. Oops, now I have so many parentheses. I'm going to put the, sorry, I'm going to write it the other way. So I'm going to replace this sine of x all squared with 1 minus cosine squared x. And then I still have this 1 sine of x left. So all of this I haven't yet integrated or used usub yet, but I rewrote the original integral using a trig identity. When you go to do the next one, I want you to think of the same idea. If we're trying to take the derivative of secant, then we need tangent in the problem, right? Because the derivative of tangent is secant squared x, and the derivative of secant is secant x tan x. So using the same idea here, we're going to use our other trig identity. And again, I don't remember them all so great, but I know this one, right? And if I divide everything by sine squared x, oops, that's not going to help me because that's going to get me cosecant. So I'm going to divide everything by cosine squared x, cosine squared x, cosine squared x, and that will get me sine squared over cosine tangent squared x plus 1 equals secant squared x. There we go, that's what I'm looking for. Well, I can use this trig identity the same way as we just did to kind of manipulate this so that I have secant and tangent in the problem. So back to our actual problem. So I haven't done any usub yet. All I did was rewrite sine cubed x as 1 minus cosine squared x times sine x. So now here when we're in class is normally the big debate. What is u? So some people say u is sine x, some people say u is 1 minus cosine squared x, some people say u is just cosine squared x, and I'm just going to debunk all those incorrect ones first. So if you said u was sine x, then your du would be cosine x dx. So then that would mean that you would have 1 minus du squared, kind of, right? And like that's not allowed. We can't have 1 minus du squared. So our u can't be sine x. Say you think your u is cosine squared x. Well then du, don't forget chain rule, would be 2 times cosine x, right? 2 times cosine x times the derivative of the inside. Well, that's not going to work. And then if you said your u was 1 minus cosine squared x, well, you'd have the same situation. So none of those three u options work. And I'm zooming us along because I'm recording this video, but normally when we're in class, people keep throwing out choices. Those are usually the three that come up. And we realize that none of those will work. So what we can do is, let's not forget that 1 minus cosine squared x is 1 minus cosine x squared. So what if I made my u real tiny and my u was just cosine x? Well, then my du would be negative sine x dx. And my only issue there is that I would then want negative du to be sine x dx, because that's what I have. I don't have negative sine. So I'm going to say u is cosine x and negative du is sine x dx. So I'm going to go back here. I'm going to erase this for a second. So here, just one of the cosine x's I'm replacing with u, and then sine x dx is getting replaced with negative du. So now my new integral, I'm going to pull that negative out front, is going to be 1 minus u squared, right? Because u was just cosine x, so 1 minus u squared, and then the sine x dx got replaced with negative du. And now I can super easily take the antiderivative. I'm going to keep that negative so don't forget it. And the antiderivative of 1 is u, right? And then the antiderivative of u squared would be minus 1/3 u cubed plus c. And I'm going to distribute that negative, so I have negative u plus 1/3 u cubed plus c. And then last but not least, replace u back. So I'm going to have negative cosine x plus 1/3 cosine cubed x plus c as my antiderivative. Okay? How does that feel? Do folks feel okay with that? Hopefully that makes a little bit of sense. And now why don't you give it a shot again on the next one using that same logic. Okay, so remember our reasoning we started out here was we had sine cubed and we needed to make cosine appear in the problem. So in our next one, we have secant x, so we somehow need tangent of x to appear in the problem. And the reason was that is because the derivative of secant x is secant x tan x, or we could even say, okay, the derivative of secant squared, derivative of tangent x is secant squared x. Either way, we need tangent to appear somehow. So why don't we use our trig identity, and maybe again, Mr. Beck made you a rock star and you knew that tangent squared x plus 1 is secant squared, but I never remember if it's secant plus 1 or tangent minus 1. So you can just take sine squared plus cosine squared equals 1. I divided everything by cosine squared so that I could get secant squared alone. So now I have this new identity. So secant squared x is equal to tangent squared x plus 1. So how can we use that to do the same idea? So I'm going to go back here, and maybe you could freeze your screen at this point if you need, or pause me. And why don't you give a shot at secant to the fourth x dx? What is the antiderivative of that? Okay, and when you're ready, hit play, and I'm going to start talking through it. So we already did this first part where we figured out what trig identity to use. So now we're going to have to replace secant squared. So I'm going to need to break up secant to the fourth x to secant squared x times secant squared x dx. So just rewriting the problem, that's equivalent. And now what I'm saying is I can replace secant squared x. So I'm going to keep one of these. I wouldn't want to replace both of them because then I have tangent in the problem and I no longer have secant in the problem, right? So I'm going to keep one of them as is, secant squared x, and I'm going to replace the other one with 1 plus tangent squared x dx. Okay, so again, remember my logic is I broke it up into secant squared and secant squared so that I could use that identity, and then obviously I can't replace both of the secant squareds with my new expression, or I won't be able to use usub. So I want to keep one of the secant squareds there, and replace the other one with tangent squared. So now I'm back to my dilemma. What's u? Well, I don't want u to be secant because that would get me the derivative of secant x tan x, and I don't have that. But again, using the same logic, our u can be something really small. What if u was just one of the tangent x? Well, then the derivative of that would be secant squared. Right? So I'm going to make my u just one of the tangent x. Another thing that helps, right, is that if you made your u something from over here, well, then you would end up with 1 plus du. And remember, we can't do that. So my u is going to be really tiny, like the last one where it was just cosine x. My u this time is going to be just one of those tangent x's. So if my u is tangent x, then my du would be secant squared x dx. So secant squared x dx, that is going to get replaced with du. So then when I rewrite my integral, I'm going to have 1 plus, don't forget it's u squared because u is just one of those tangents, 1 plus u squared du. And then I can find the antiderivative, which is going to get me u plus 1/3 u cubed plus c, and then replace back. So I'm going to end up with u was tangent x plus 1/3 tangent cubed x, or you can write tangent of x cubed, plus c, final answer. And if you practice and you took the derivative of this, you will get secant to the fourth x. I'm not going to do it to make this video longer than it needs, but maybe you want to practice, take the derivative of this. It'll help you review your derivatives of trig functions and your derivatives of using chain rule. And you simplify it, it does equal secant to the fourth x. Okay. Next one. This is one you could probably do on your own. I just wanted to toss it in here because I feel like we've talked a little bit about like when do you pick something from the numerator, when do you pick something from the denominator, when do you know to use the whole thing. So again, it does take a little bit of practice. You can always try one, and if it doesn't work, try the other. Excuse me. So why don't you pause, give this one a shot, and see what you can do. And then when you come back, I will talk through the correct answer. Okay, so I'm always going to start with my logic. Okay, let's pick u from the denominator. So let's say u is 7 plus e to the 2x. I like to include constants if I can. I want to back you up. I could not include the 1. I could not include the 1 here. Because remember, 1 plus tangent squared x is not the same as 1 plus tangent of x squared. So I can't make my u 1 plus tan x. It doesn't work, that math isn't right. So here though, it might be helpful to take the 7 as part of my u, because then the derivative of it, the derivative of 7 is 0, and the derivative of e to the 2x is 2e to the 2x dx. So far looking pretty good. I can have this be my u, and then I want e to the 2x dx by itself. So if I divide by 2 on both sides, I'll have 1/2 du is equal to e to the 2x dx. So here's my u, here's my du. So I'm going to replace this back. So e to the 2x dx got replaced with 1/2 du. And then in the denominator, I have 1 over u. Right, that's a common mistake too, is people just write u, right? So the u is in the denominator, so I have 1 over u. And then the e to the 2x dx got replaced with du. And now if I take the antiderivative, I'm going to have 1/2 times the natural log of the absolute value of u plus c, and replace my u back, 7 plus e to the 2x plus c. Final answer. Okay, and now for our last one, we're just going to talk through one definite integral together. Obviously, I asked you to watch that video, but again, maybe just a little bit of practice here. This also connects back with our 3 methods. So I don't know the antiderivative of cotangent, right? I know the derivative of cotangent, but I don't know the antiderivative. Of the 6 trig functions we know, none of them have a derivative of just cotangent. So that means I don't know the antiderivative of it. I can't use reverse power rule, so I'm going to need to use usub. So I think we talked at the end of last class, and that's kind of why I picked this problem as a twofer, that we can rewrite cotangent of x as cosine of x over sine of x dx. Okay. So then from here, I'm going to need to use my u substitution. So I'm going to, again, stick with my logic of let's try u as the denominator first, because I can't have du in the denominator. So I'm going to say u is sine x, and then this works out perfectly that my du will be cosine x dx. So now I can go and replace this integral, right? This is going to be du. So I have 1 over u du. So then part of what they talked about in the video is, remember, these bounds in the original problem were related to x. So that means that since your new integral pertains to u, we need to change the bounds to be about u. And this will make it so that we don't have to replace the x's back. We can just evaluate the integral and sub in the u values instead. So we had originally that x was going from pi over 4 to 3 pi over 4. And now in our new problem, we need to replace those with u. So why don't you take a second to think about, okay, how can I use this expression if u is equal to sine of pi over 4 and u is equal to sine of 3 pi over 4? How can I figure out what our u bounds are? Right, so sine of pi over 4 is going to give me root 2 over 2. And sine of 3 pi over 4, well, 3 pi over 4, I'm now in 1 pi over 4, 2 pi over 4, I'm now in the second quadrant. So sine's still positive, so sine of 3 pi over 4 is also going to give me root 2 over 2. What did I do wrong? Sine of pi over 4. I feel like I just picked a weird problem. I think I just made a mistake, friends. I'm sorry. I was like, I'm not going to do these problems before because that's just too much work to do them all and then do a video talking through them all. And so I just made this one up on the spot. And then I realized I did something silly. So I did. I should have picked something different. My bad. But hopefully we're all smart enough. I just want to say one thing, right? That the answer to this is going to be 0, right? Because we haven't accumulated anywhere because we went from root 2 over 2 to root 2 over 2. And when you go to substitute those in and subtract them, you'll get 0. But since we want to actually practice a little bit, let me just change one of these. So what if I made this pi over 2? Let's do that. Pi over 4 to pi over 2. So then let's do this would be, pi over 2. So then this would be sine of pi over 2, which would be 1. So then this would be 1. Okay, there we go. So now when we try, hopefully this works. The antiderivative of 1 over u is going to be natural log of u. And now my bounds are about u. So I don't have to replace the u back. I'm going to go from root 2 over 2 to 1. And now I can substitute it in, and I'll have natural log of 1 minus natural log of root 2 over 2. And final answer, right, natural log of 1 would be 0 minus natural log of root 2 over 2. So this is going to equal negative natural log of root 2 over 2. And root 2 over 2 is positive, so I can just leave it like that. I apologize for you. I am going to change this on yours so you don't have to do the wrong problem first. So you're going to be like, why is she doing a different problem than me? But then you'll realize what I realized. So hopefully that was all good. Sorry if I added some extra confusion in there at the end. Let me know if you needed anything. See ya.